Hi everyone, welcome to section 10.3 where we introduce the law of sines. Now we need to have a new law to solve for different or missing pieces of a triangle because sometimes the triangles we're given are not right triangles. So if we have a triangle that is not a right triangle, we consider that triangle to be something oblique. So an oblique triangle by definition is any triangle that is not specifically a right angle triangle. So it does not have a 90-degree angle in it. So oblique triangles can be one of two types. They can either be acute, which means that all angles inside that triangle are measuring less than 90 degrees, or you have something we know as an obtuse triangle, which means that one angle measures something greater than 90 degrees. So if I were to draw some examples of acute and or obtuse triangles at the bottom of the page, we might see something similar to this and call that an acute triangle because we can see that the three angles are measuring somewhere less than 90 degrees. And then we can draw what we know to be an obtuse triangle. So that first angle that I'm creating is obviously larger than or greater than 90 degrees. So this would be considered obtuse. So the sine law is going to help us solve for missing angles and solve for missing sine lengths for acute and obtuse triangles. The reason why we need other laws is because we're not allowed to use Pythagoras' theorem unless we have a right triangle, and we are also not allowed to use the sine, cosine, tangent ratios, SOHCAHTOA, when we have a triangle that again is not a right triangle. Before we get into the actual sine law, what we want to focus on is what I will consider to be triangle orientation. So you are going to be given three pieces of information in order to solve a triangle. Now, one of those pieces of information needs to be a side length. If you don't have at least one side length, then you won't be able to accurately determine what the angles inside those triangles are going to be. So we need to have a side length given, and then we need two additional pieces of information. What you have here are different options for orientations. I want you to note that in this list, A denotes that you have a given angle, and S denotes the fact that you might be given a side length. So what I'd like to do is draw each of these orientations out to show you the types of triangles you might be working with and how to sort of decode this triangle orientation. So the first set of given information that we see here is three angles. So that would be angle, 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 or AAA. And again, if we were to solve a triangle, we would need at least one side length. So we're not going to be solving with triangles that are giving us this information, but I'm going to use the symbols alpha, beta, and theta in order to denote these missing angles. So maybe you have alpha given to you, you might have beta given to you, and you might have theta given to you. So this would be an example of an AAA orientation triangle. Now, because we can't solve triangles that have no sides given to us, it's more important that we focus our attention on the other five orientations that you see at the top of your page. So if we are given an AAS orientation, what that means is we have two angles and a side. But what's very clear about this is you need two given angles and a side that is not between those two angles. So if I were given angles alpha and beta, a side length that I might be given might be sitting here along the top side. So I'm going to put a tick through that side length showing you that I've been given a side, but that side is not sandwiched between the two given angles. So this might be a representation of an AAS triangle. Next, we have an ASA triangle. So once again, we have two angles and a side, but this time the side positioned is in between the two angles that are given. So you might have angle alpha, you might have angle beta, so same as the previous triangle, but we might be given the side between those two. So the orientation of this is ASA. So we have an angle, side, and angle in a row. Next, we might have SSA, which means we have two sides, and in those two sides, we have an angle sort of outside of those. So we might be given a side a length of, let's say, one tick here, We might have a different side length here, so a second side that was given to us. And then if we choose an angle, it has to be an angle that is not positioned between those two sides, because you can see that in order this is SSA, so we have a side, and then the angle not between those sides. So I might see something like this. So once again, we have two sides and an angle, but within SSA orientation, the angle cannot sit between those two given sides. If you have an SAS orientation, it means you have two sides and an angle again, but this time we see that the angle is sandwiched between those two given side lengths. So we might have side 1, we might have side 2 given to us, but this time alpha, or the angle given to us, is going to sit right between those two sides or connect them. So that would be an SAS orientation. Last but not least, we might give you 3 side lengths. So if you're given side length 1, side length 2, and side length 3, you would have an SSS orientation. Now it's important for you to note that these orientations can change from one example to the next, but it's also important for you to note how these orientations work together, because the sign law is going to be used for very specific orientations only. So the sign law can be used if your given information is AAS, ASA, or SSA. So what you see is you'd have two angles and a side that's not between those angles. You might have two angles and the side between those two angles, or you might be given two sides and an angle sort of opposite. Now, in order to use what we call the sign law, you have to have one angle and the side, or one side that is opposite that given angle. So if you don't have a pairing of an angle and a side opposite, you will not be able to use the sign law. You're going to have to use a different law that we'll explore later in this module. You'll often see the sign law written one of two ways, and before we get into these actual laws, I just want to remind you that if you see lowercase letters, those are side lengths, and uppercase letters are always there to denote angle measurements. So if we take a peek at the first variation of this sign law, we see that if you have a side length A divided by the sine of angle A, that's equivalent to side length B divided by the sine of angle B, which is also equivalent to side length C divided by the sine of angle C. Now, you're not necessarily going to be using all three parts in this equation. You're going to be using any given two at a time. So you might be using A, let's fix that here. You might be using A divided by the sine of angle A, and then you're comparing that to side length C divided by the sine of C, let's say. So if we were dealing with angles and sides that are A's and C's, we would pick those two parts of the sign law to carry out our plan and to solve. Now, the second variation of the sign law is exactly the same equation, but we have switched the location of the numerator and denominator. So sine of angle A divided by A is equivalent to sine of angle B divided by B, which is equivalent to sine of angle C divided by side length C. So it doesn't matter which formula you use. You can use the one on the left or the one on the right, but again, you'll be using 2 out of 3 of these parts to solve for missing sides or angles. So if we want to solve in our first example triangle ABC with A measuring 43 degrees, we have B measuring 98 degrees, and we have side length C measuring 22 meters. Now, as we did with previous triangle solving questions, so when we asked you to solve triangles previously, we said it was a good idea to draw out not only your given information, but to draw out a chart that can be filled in so we know when our solution is complete. So we know that A was 43 degrees. We know that angle B measured 98 degrees. C is an unknown, so we can leave that blank for now. Side length C was 22 meters. B as a side length is unknown, so I'm going to leave that blank. And side length A is also an unknown. So we have three different things we need to solve for in this particular triangle. Now, it's often also a good idea for us to make a quick little sketch. What I hope you recognize right away is this is not a right triangle because B on its own is measuring 98 degrees. So we have an obtuse triangle here. So if I were to draw my obtuse triangle, looks maybe something like this. I would say that angle B measured 98 degrees. We have A and C, which we're not really sure which is which, but it doesn't matter as long as we mark our sides opposite correctly. So angle A might be measuring in this upper left-hand corner, and we'll say that that's 43 degrees. But side length C is 22 meters. So remember, the side length is always opposite the angle with the same name. So lowercase c, or 22 meters, will sit along this side of your triangle. So if we pay close attention to the orientation that we are given or we're starting to work with, we have two angles and we have the side measured between them. So we say that this is an angle side angle orientation. If we have an angle side angle orientation, it means we are ready and can use the sine law. So the only other piece of information we want to be very mindful of is that when you're using the sine law, you need to have a side and angle that are opposite one another. So a side and its opposite angle, or vice versa, are needed to proceed. In this case, it kind of looks like we don't have enough information, but if we have side length C, we need to hunt down the answer or solution for angle C. And we can do that very quickly because we know the sum of all three angles inside this obtuse triangle are going to be 180 degrees. So if I wanted to solve for angle C, I would take 180 degrees and subtract the two angles that were given. So we can subtract 98 degrees and we could subtract 43 degrees. So when we do that, make sure you include your degree symbols here. When we do that, what we get is a total of 39 degrees. So angle C is going to measure 39 degrees. Now we have an angle and a side opposite, and we know with any angle and side opposite in these situations, we are allowed or can use the sine law. What you need to do next is choose a side length that you're looking to solve for. So if we go alphabetically, I might want to solve for A first. If I want to solve for A first, then the portion of the sine law that's necessary is going to be A divided by sine of A, or sine of angle A. Now, if I said, let's set that equal to B divided by the sine of B, the problem is that equation would have too many unknowns because I don't know what side length B is measuring. So in this case, we must use C divided by sine C as the other half of our equation. So now we get to substitute the information that we know at this point. We know that A is an unknown, so we can leave it as A. We're dividing that by the sine of angle A, or the sine of 43 degrees. And that's equivalent to C, or 22 meters, divided by the sine of angle C, so the sine of 39 degrees. To solve an equation like this quick and easy, you can use the cross multiply and divide sort of technique, or if you prefer, you can clear fractions and work from there. But if A is my target, if I'm trying to solve for A, what I'm going to do is multiply the two things that are diagonal as given pieces of information. So I'm going to multiply 22 by the sine of 43 degrees. So we're going to cross multiply and then divide by whatever we have left over and haven't used yet. So we're going to take 22, multiply it by the sine of 43 degrees, and divide that by the sine of 39 degrees. And that's how we can manipulate this equation and solve for A. Again, if you don't want to use cross multiplication and division in order to solve these, you're welcome to clear your fractions. So you can multiply both sides by the sine of 39 degrees and the sine of 43 degrees in order to solve as well. Another technique that might be rolling around in your mind, if I kind of reset this equation, if I have a over the sine of 43 degrees, and I know that that's equivalent to 22, all divided by the sine of 39 degrees, we can use cross products and say those two terms, so a times the sine of 39 degrees, would be equivalent to the sine of 43 times 22. So we could go 22 times sine 43. Always be mindful that the angle is held separate from the side length, so you're going to have to be mindful of brackets here moving forward. Now, if I wanted to solve for a, once again, we can divide both sides by the sine of 39 degrees. And we land in exactly the same spot as using cross multiplication and division. So a is exactly 22 times the sine of 43 degrees, all divided by the sine of 39 degrees. So be careful when you're typing this into your calculator. You're going to literally type in 22 times the sine of 43, and then you want to make sure you close your bracket when you close that angle of 43 degrees, and divide that then by the sine of 39. So what you should get for an A value is approximately 23.8 meters in this case. So we've got an A value of 23.8 meters. I'm just going to fill that in to my chart here. And the only other piece of information now we're looking for is side length B. It would be very illegal for us to use Pythagoras' theorem because Pythagoras' theorem is reserved for right triangles. We can't use SOHCAHTOA either because, again, SOHCAHTOA is reserved for right triangles. So what we have to use in this case is another portion or set of ratios from our sine law. So if we're hunting now for side length B, we can use B divided by sine B as half of our equation. Now, truth be told, we have all of the information for A and we have all of the information related to C, but it's smarter for us to choose C in order to use and solve with, because C was information that was essentially given to us. We didn't have to solve that. So if we, by mistake, did something funky with our calculation of A, we don't want to sort of let that mistake cause a ripple effect and give us more mistakes in our work. So we're going to use B divided by sine B and set that equivalent to C over sine C. So B is the side length we're searching for. We can divide that by the sine of 98 degrees and say that that's equivalent to 22 meters divided by the sine of angle C, which we know to be 39 degrees. So once again, I'm going to cross multiply and divide. So I'm going to take 22 times the sine of 98 degrees and divide that by the sine of 39 degrees. So again, you can use whichever technique you are most comfortable with. You can use cross products or clear your fractions. Any method from here is appropriate as long as you're using brackets correctly and you're being very mindful of whether or not you're using sines or side lengths. So 22 times the sine of 98 degrees divided by the sine of 39 degrees. So you literally type what you see. You'll get a B value of approximately 34.6 meters. So if we take a look at our table, we've filled in all of our missing measurements, and at first glance we notice that the smallest angle is across from the smallest side and the largest angle is across from the largest side, and that's what we should anticipate when we solve these types of triangles. So example number 2 gives us a new triangle to solve, and it says solve triangle ABC with angle C measuring 102.3 degrees. We have measure of angle B as 28.7 degrees, and we have side length B measuring 27.4 centimeters. Once again, at this stage, we want to build a little bit of a chart so that we know what information is missing and what information we've been given clearly labeled. We've got angles A, angle B, which we know is 28.7 degrees, and angle C, which is 102.3 degrees. And then we have side length A, which is an unknown. we have side length B, which measures 27.4 centimeters. And once again, C is also an unknown. What you'll notice is I use approximations for unknown values because chances are pretty good that we're going to have to round those values when we find them. So from here, we also want to draw our triangle. Very rough sketch is all we need. Now, we recognize right away that this is another obtuse triangle, so we want to make sure that we draw that obtuse angle, something measuring greater than 90 degrees here. So if that's angle C and it measures 102.3 degrees, then we can label A and B as well. So angle B in this case is 28.7, and we've got side length B of 27.4 centimeters. So side length B is going to be opposite angle B. So we know 27.4 centimeters is sitting in this location the way I've drawn and labeled my current triangle. So what I have in this case are two angles and a side, but this time the side is not sandwiched between them. So we need to call this an AAS triangle, or you can say SAA, but as long as we are noting in this case that the side is not sandwiched between those two angles. So that being said, this is another triangle that we can solve using our sine laws. So when you're using a sine law, you need to make sure you have an angle and a side opposite, and we see that angle B and side B are already given to us. So it now becomes our choice for where to go and solve next. And I would say that solving for angle A is probably the easiest thing for us to do first. So angle A is going to be found by taking 180 degrees. We know that the sum of all three angles in this triangle are going to be 180 degrees, and we could subtract the other two given angles. So we're subtracting 28.7 degrees, and we're also subtracting 102.3 degrees. So if we carry out that subtraction, what you get is 49 degrees as angle A. So we can put that into your chart. We know that's given information, or information that we've been able to find using the information that we are given. Now, if you want to solve alphabetically, let's say you want to find side length A, then if you want to find side length A, we need to use A and sine A as the first part of our equation. So we've got A divided by the sine of angle A, and that's going to be equivalent to two given pieces of information. We have all of the information associated with B, so we can use B and sine B as the second half of our equation. So A divided by sine A now becomes A divided by the sine of 49 degrees, and B divided by sine B is going to be 27.4 centimeters divided by the sine of 28.7 degrees. So from here, once again, we're trying to solve for A, which is our unknown, and what we can do is cross multiply and divide. So once again, when we solve for A, that's going to be 27.4 multiplied by the sine of 49 degrees, and we divide that all by the sine of 28.7 degrees. So I just did some cross multiplication and division. So when we work this out, what you'll get for an A value is approximately 43.06, or we would say 43.1 centimeters as your length. We can see right away that that's bigger than side length B, but that makes good sense because angle A is larger than angle B. So far things are looking pretty good. Now if we want to solve for C, the part of the sine law that we're concerned with now is C divided by the sine of angle C, and we know that we can set that equal to B over sine B. So the B value we're given is 27.4 centimeters divided by the sine of 28.7 degrees. And I guess we can insert what we know for angle C here as well. I should have done that initially, so let's rewrite that here. We've got the sine of angle C, which we know is 102.3 degrees. So once again, when we solve for C, we need to cross multiply and divide. So we're going to take 27.4 and we multiply that by the sine of 102.3 degrees. and then divide that when we're done by the sine of 28.7 degrees. So be very careful here. You've got 27.4 multiplied by the sine of 102.3 degrees, and then you're dividing that by the sine of 28.7 degrees. So make sure you're in degree mode at all times so that the C value in this case turns out to be roughly 55.7 centimeters. And once again, that answer makes good sense because the largest angle should be across from the largest side. So 102.3 degrees is definitely the largest angle, and 55.7 centimeters is definitely the largest side length. Now that our chart is complete, we found all missing side lengths and all missing angles. We have completely solved this triangle. With example number 3, we now have a new set of given pieces of information. So we know that angle A measures 110 degrees. We know that side length A measures 15.2 centimeters. And we're also given side length B measuring 20 centimeters. So once again, we can set up our chart over in the right side margin here. We've got A, B, and C. We've got 110 degrees. Angle B is unknown and angle C is unknown. Side length A was given as 15.2 centimeters and side length B was given as 20 centimeters. So what we can do is draw another obtuse triangle because we're given an obtuse angle here to work with. With this obtuse triangle, we know angle A is measuring 110 degrees, side length A is 15.2 centimeters, and side length B, it doesn't really matter which way we label here, side length B is measuring 20 centimeters. So once again, when we're using sine law, we need to pick an angle and a side that are opposite, but we should be mindful of the type of orientation we're given. So we have one angle and two sides. The angle is not sandwiched between those two sides, so we have to say that this is a side-side angle triangle. So we do have an angle and its side opposite, so it's definitely in line with our use of the sine law. And we can see that because we're given all of the information for A, we can say that A over sine A is going to be part of the equation we use to solve. Now, we have no information for C whatsoever, so we're going to park C and just leave that for a moment. And we're going to set this equal to B over sine B so that we can at least find the missing angle or angle B. So if we plug in the information that we know, we have 15.2 centimeters divided by the sine of 110 degrees, and that's going to be equivalent to 20 centimeters divided by the sine of angle B. So in this case, we're not solving for a side length, we're actually solving for the sine of angle B. We'll get the angle out of that by using an inverse function, but we're trying to solve for sine B. I can still use cross multiplication and division and say that if we want to solve for sine of B, we can take 20, multiply that by the sine of 110 degrees, and divide that by 15.2 units. So it's very important here that you're being mindful of whether you have side lengths or whether you have angle measurements that are corresponding with those sine values. When we do the calculation for this, you see that the sine of B is roughly 1.2364. Now that's a ratio, that's not an angle measurement. Remember, when we're given the sine of B or the ratio, we can use sine inverse to find the actual angle. So the step we want to take here is to say that the angle B is going to be found using sine inverse of 1.2364. So when you type this into your calculator, you're going to have something very funny happen. So sine inverse, remember, is that second function. And what you're going to get here on your calculator screen actually says error. There's a big problem with this. The error is that it's telling you it's a domain error. But let's look closely at the type of triangle we're drawing and how the measurements were given to us. See if we can find out why this is actually giving us an error. There's actually no angle here. So no angle exists with that ratio. So let's do a little bit of digging and see if we can't explore why. If I look at my given information, and I start with angle A and side length A. Angle A is 110 degrees, which is an obtuse angle. What we know about obtuse triangles is that only one angle can be obtuse. Now we've got a side measurement of 15.2 centimeters, but if we look carefully at what's happening with B right underneath, the side length for B is actually 20 centimeters. It's actually bigger. So that would mean that angle B would have to be bigger than 110 degrees, and we know that that's just not possible. So there's no real triangle solution here. We don't have measurements that would lend themselves to triangles. So we would have something, if I were to sketch this information, we would have angle A measuring 110 degrees, so we can kind of draw our angle A. But angle B would have to be measuring more than 110 degrees. So it would be another, if angle B were here, let's say, it would be another obtuse angle. Well, that's never going to join sides and make a triangle. So we can see, now that we've started to sketch it more to scale, that angle B just isn't going to work in this case. So what we get here by seeing that there's an error in angle B, or in the calculation of angle B, is that there's actually no solution here. There's no triangle that we can build based on the information we're given. So on occasion, you're going to get a triangle that can't be solved. This is how that happens. You have a side length and an angle measurement that aren't really corresponding to what we think those measurements should be. So once again, we want longest side across from largest angle, and we can see that that's not going to happen in this case because we cannot have two obtuse angles in the same triangle. So we have one more example to try and solve, and we're given this time angle A of 110 degrees. We're given side length A measuring 48 centimeters, and we're given side length B measuring 16 centimeters. So once again, when we start to build our chart, this one looks a whole lot better. We've got 110 degrees across from 48 centimeters. That's a pretty big side when we compare it with what we have for side B, which is only 16 centimeters. So we can see for sure so far that 110 degrees is the largest angle, and so far that is the largest side opposite. So we're looking for C, we're looking for angle C, and we're looking for angle B as well in this type of question. Now once again, let's draw out this triangle, see what our given information looks like, or what orientation we're given, and then we can solve from here. So we've got angle A measuring 110 degrees. We have angle B, which is unknown, but side length B is 16 centimeters. And we have angle C, which is unknown. And the only other measurement that I'm missing now is side length A, which we know is 48 centimeters. So we see we have two sides and one angle, but the angle is not sandwiched between those two sides. If it were, we'd have angle C. But in this case, we can see that that angle is outside of those two sides. So we have a side-side angle orientation. So with a side-side angle orientation, we're ready to go ahead and use the sine law. So once again, we have all the information for A, so we can use A over sine A, and that's equivalent to, we're going to set it equivalent to B over sine B, because at the very least we have side length B, but not angle B. So this will give us three important pieces of information, so we can solve for that fourth missing piece of information. So you've got 48 centimeters divided by the sine of 110 degrees, or angle A. That's equivalent to side length B, which we know is 16 units, divided by the sine of angle B, which is, again, our unknown. That's what we're trying to solve for. If that's our unknown, I can still use cross products. So I can cross multiply and say that the sine of angle B is going to be 16 times the sine of 110 degrees, and then I'm going to divide that by 48. So I'm going to divide by the side length of 48 units, not the sine of 48, just 48. So the sine of B, now be careful with your calculator, is going to be 16, you have to be very careful with this, 16 times the sine of 110 degrees, and then close the bracket after 110 degrees, or get an answer, and then divide that answer by 48. So what you should get for sine of B is approximately 0.3132. Now, that's the sine of angle B. We want the actual angle for B. So to calculate an angle when you have a ratio, we have to use sine inverse. So the sine inverse of 0.3132 gives you, now what you can do is one of two things. You can retrieve your answer, or you can go sine inverse and type in 0.3132. Both of those would be okay. This gives us roughly 18.3 degrees as the angle measurement for angle B. So we can fill that into your chart as well and say that's roughly 18.3 degrees. And now that we have 2 out of 3 angles, we can go ahead and find that third angle using subtraction. We're going to need that third angle before we can solve for side C anyway, so we might as well do that here. Angle C is going to be 180 degrees, which is the sum of all 3 angles, minus we have 110 degrees for angle A, so 180 minus 110, and then we're also going to subtract our newfound angle of 18.3 degrees. So when you subtract all of those measurements from 180 degrees, we get angle C measuring 51.7 degrees. So we can fill that into your chart as well. We have one more piece of information to find, and once again, we can use the sine law in order to do that. I'm going to go back and choose A divided by sine A because that was our given information right from the start, and we're going to set that equivalent to C divided by the sine of angle C. So from here, we know A is 48 units. We have the sine of 110 degrees in the denominator here because that's the sine of angle A. We're going to be finding side length C, but we know that the angle measurement for C is 51.7 degrees. So we have C divided by the sine of 51.7 degrees. Once again, C is my unknown, so I want to cross multiply and divide. So C, or my side length, is going to be 48 times the sine of 51.7 degrees, and then we can divide that by what we haven't used up yet, which is really the sine of 110 degrees. So once again, we can cross multiply and find that answer and divide. So 48 multiplied by the sine of 51.7, close that bracket, and then divide by the sine of 110 degrees gives you 40.1, roughly speaking. So C is approximately 40.1 centimeters. So we can fill that into your chart and make sure that all of these side lengths and opposite angles make good sense and are sort of proportional to what we would imagine. So the largest angle is 110 degrees. The largest side is across from it, 48 centimeters. We also recognize that the smallest angle is 18.3 degrees, and that's across from the smallest side of 16 centimeters. So once again, we have solved this triangle and found all missing pieces of information. So the trick or takeaway, I guess, to 10.3 is to make sure that when you have a triangle that is not a right triangle, so if you have an acute triangle or an obtuse triangle, you're going to need to use the sine law. On top of that, we want you to be mindful of what orientation you have or you were given for information. So for example, this was a side-side angle triangle, because when we learn about the cosine law next, we're going to be using the cosine law in very specific situations or scenarios. So have a look at the homework questions here in 10.3. Make sure that if you have any questions as you're going through the homework, you bring those questions forward so we can help you sort them out before we finish up the module.